Hello everyone, my name is Alvaro, and in this video I will be solving another problem from the Blind Leetcode 75 problem list. Today I will be doing problem 153, which is called Find Minimum in Rotated Sorted Array. So let's get to read the problem statement. Suppose an array of length n, sorted in ascending order, is rotated between 1 and n times. For example, the array nums right there might become this array right here or this array right here. And then if we rotate this one time, it simply means that we are moving the last element to here. So that's pretty much why it's telling us that. Given the sorted rotated array nums of unique elements, return the minimum element of this array. You must write an algorithm that runs in O of log n time. Obviously, we can think of a super easy solution, and that would be to simply just loop through the entire array and find the minimum, but obviously that takes O of n time, and we want to improve that. So that's why the problem statement is just telling us this right now. So let's take a look at the examples. We have this right here. Obviously it's 1, and here it's 0, and here it's 11. So those are some inputs that we might see. So yeah, if you've never done this problem before, now I suggest that you stop the video, think a little bit about it yourself, because I'm going to start explaining the solution right now. So the main idea here is to use a slight modification of binary search. Usually, whenever you see something that runs in O log n time, especially with arrays like searching something, thinking about binary search might be a good start, because binary search is one of the most common algorithms that you'll use to find elements in a sorted array, since it can find them in log of n time, which is vastly more efficient than big O of n. So let's cover how we would implement binary search just really quick. So suppose that we have the original array here. The main idea behind binary search simply is to have a left and a right boundary, right? Whenever that happens, we find the midpoint between these two boundaries, and the midpoint in this case will be this one, right? And depending on what we want to find, we will either go to the right part of this array or the left part, where the left part is defined by the left boundary. The new left part will be a part where the left boundary is the original left boundary, and the right part is the current element. And the right part will be a part that's defined by the original right boundary as its right boundary, and the current element as its left boundary. So the idea is to just shrink the size of the subarray by n over 2 every time, where the subarray size is n. And that's how you get a log of n time. So how can we modify this algorithm to solve this problem? So here I'm just going to write a couple of examples with like rotated versions of this array that will kind of tell us like the different cases that we can handle. So let's think about this one, for example. All right. So 2, 4, 5, and 6. Okay. And then for this one right here, we will start with a 2, 4, 5, 6, 7, and then a 0 and a 1. So we'll focus on these two as of right now. And then I'll also write down the one in which it's in the middle. I think this one will help as well. So we have, it's right here in the problem statement too. So 4, 5, 6, 7, 0, 1, 2. I meant to say next to the number that's in the middle. So let's get to it. So what we can do, right, the way that we can modify this binary search is by looking at the values of the boundaries and comparing them with the value of the midpoint, where the midpoint is the current element that I was talking about before. So the original here will be just the one in the middle, right? The main idea is this. We know that the array is ascending, right? So if right now, right, we always start with the left boundary being in the first element and the right boundary being in the last element. Whenever the right boundary is greater than the element located at the midpoint, we know that all this chunk is going to be increasing. Therefore, what we will do is just simply go over to the left part of the array. Converse, like in the opposite case, right, will be this one. Whenever the right boundary is smaller than the element located at the current midpoint, that means that the smallest element will be on the right. Because the only time in which an element that goes after another one is smaller is whenever we have gone from one element to the minimum. So what I mean is, if you are at any location I, right, where I is an index, the only time in which I plus 1 will be a number smaller than I in the array is whenever we've encountered the minimum. So this one right here. So the only case if we're at I, right, and this is I plus 1, we can pick any I, and the only time in which I plus 1 is smaller is this one. So because of that here, we know that at some point in this right subarray, right, we have the minimum, which has made the right boundary smaller than the current element. So that's the main idea. Pretty much if num sub right, because remember right is just an index and we're using just this right here. If the nums sub right is bigger than the nums midpoint, then we will go to the left in our recursion. I'm going to implement this problem recursively. You can certainly do that iteratively, but I think it's easier to understand recursively, at least binary search in my opinion. So then and the other case is if nums dot right is smaller than nums midpoint, then we will go to the right. So that will be this case right here. Now, when do we stop the recursion, right? What are our base cases? Well, we have two. The first one will be whenever the left boundary is equal to the right boundary. Whenever that happens, that means that the current subarray is of size 1. And as a base case, well, it's easy to see that whenever we have a subarray of size 1, then the smallest element in that subarray is the only element in that subarray. So whenever left is equal to right, then we simply return the number nums sub left or sub right. Like it's the same thing, which is the same as num sub right. Now, the other base case will be this one right here, and this is why I highlighted this element in the problem statement, because I think it does a good job with it. It's whenever we have found an element such that num sub I is smaller, or sorry, not smaller, bigger than nums sub I plus 1, right? In this case right here, like I mentioned before, the only case in which this happens is whenever num sub I plus 1 is the smallest the minimum in the list, in the rotated list. Because remember that it is ascending. So the only time in which it will be smaller is whenever we have the minimum. And in this case, we just return nums sub I plus 1. And that'll be pretty much our code. Like I said before, you can implement this iteratively, but I think it'll be easier to read and understand if I write the recursive way. I'll leave it to you as a personal challenge to write it iteratively if you want, but I'm going to get to write down the code right now. So for this, I'm going to use a helper method. So I'm just going to call it helper. And simply what we're going to do is we're going to pass the parameters that we would use in a regular binary search, which is the left boundary, the right boundary, and the original array itself. Now, let's think about the base cases. So we wrote them down here. So whenever left is equal to right, then we simply return nums.left. You can also say nums.right. It really does not matter because remember, left is equal to right in that case. I just wrote down left because I guess it has one less letter, but it really doesn't matter at all. Now, whenever we have found this, right, we simply return, but now we need to find the midpoint. So what is the midpoint? Well, Keep in mind that we always need to use integer division for this because we are dividing two numbers that can add up to an odd number, and when we divide that over 2 we get a float. And obviously you can't access indices whenever your number is a float. So the midpoint between these two numbers is simply the floor of whenever you add up these two numbers and divide them over 2. So left plus right over 2. So, the midpoint formula. So this will be the midpoint right here. And once we've calculated the midpoint, we can check this other case where I, right, is the midpoint. So what we can say is if nums sub midpoint is greater than nums sub midpoint plus 1, then we simply return nums sub midpoint plus 1. Because as we have covered before, the only case in which the number that comes after is smaller is whenever that number is the minimum. And now we will simply do the traversal of the array. So the other cases that we have is, let's go first with, I don't know, let's do this one right here, the one in which we go to the left. Okay, so if nums dot right is greater than nums midpoint, we go to the left. And what does going to the left mean in our code? Well, like I mentioned before, right, going to the left or to the right is determined by the boundaries. So we're going to move the boundaries around. So whenever we go to the left, we will use the helper method, right? Oh, sorry, the parentheses should be here. Whenever we go to the left, the current left boundaries are kept the same. But now in the new subarray, the right boundary becomes the current midpoint. That way we don't go anywhere anymore to the right. Just like you would do in a regular binary search, The other case simply is this one right here. Sorry, not this one right here. It will be this one right here, the one in which we go to the right. In which case, we simply return helper. And now, in the previous one, right, whenever we go to the left, we change the right boundary. But since we're going to the right, now the left boundary is the midpoint. The new left boundary is the midpoint, and the right boundary is kept the same. And that'll be pretty much it. After that, we simply just have to return the helper, and we start with 0 because that'll be the first element in nums. And then we just simply pick the last index. So that'll be the length of nums minus 1. And then we just pass the regular array itself. And this solution should work. There you go. And I've tested this solution. It eventually even gets down to like 17 milliseconds, which beats like 99% of the solutions. But this is good enough for the video. So what is the runtime complexity of this solution and the spacetime complexity of this solution? Well, the runtime complexity of this solution is big O of log n time because we are shrinking the size of the array by n over 2 every time. Therefore, we are going to look at most, log base 2 of n numbers. And what is the spacetime complexity? Well, since we are using recursion and we are looking at most at big O of log base 2 of n numbers, and in each recursion we look at one different number, then the spacetime complexity is also big O of log n. But I would say this is a good enough solution. It's definitely fast. But if you want to challenge yourself and use a solution that uses big O of 1 spacetime complexity, then do the iterative method. But in this video, I just wanted to highlight the way to do this because I think the concept itself will be like the concept itself of like the binary search, the modified binary search is more important for the viewers to understand. And I think the recursion makes the code more legible. So if you want to challenge yourself and do the iterative way, then I definitely recommend that you just, after this video, just go and do it yourself. But yeah, that's pretty much it. I hope you liked the video. Make sure to drop a like, which helps the channel a lot. And see you in the next one. Bye-bye.